Okay, kids, we're back. Section 8.4 of the textbook, Ampere's Law. We're going to go through Ampere's Law, sort of go through Ampere's Law. This is one of the most important laws in physics. It's amazing. But the complete explanation requires, you know it. How many times have I said this? Calculus. And this part, integration part of calculus. So we'll do the best we can. So I want you to remember something. That if you got a straight wire with a current going through it, magnetic field is created around this wire. You can see the compasses here helping us map out the magnetic field. And we use our right hand to get the direction of the magnetic field, which is a bunch of concentric magnetic field lines all around. Now you see how the magnetic field lines are closer near the wire? That's because the magnetic field is stronger there. The further you get away from the wire, the weaker the magnetic field. The actual strength of the magnetic field, the magnitude of it, depends on how much current is in the wire and how far you are from it. This is a proportionality sign. If you want to change it to an equation, the strength of the magnetic field, its magnitude, is equal to some constant K times the current divided by how far away you are from the wire. Now you shouldn't be afraid of this constant here that eventually we're going to have to figure out what it is, because you've seen other constants, right? Big G for universal gravitational constant, K for the electrostatic constant. So you've seen it before. We just got to figure out what it is. And that's where Ampere's law comes into play. So this is straight out of the textbook. I'm going to read for you what it says here, Ampere's law. I'm going to read it through first, and then we'll break it down. Ampere's law. Along any closed path through a magnetic field, the sum of the products of the scalar component of the vector magnetic field is parallel to the path segment with the length of the segment is directly proportional to the net electric current passing through the area enclosed by the path. Well, of course it is. Why? I thought you said this was going to be complicated. Mr. Shapiro, well, I got it. I understand it completely right now. Well, I know I didn't my first time looking at Ampere's law, so I'm going to try to break this down for you. First of all, along any closed path through a magnetic field. Let's just deal with this part. Here's a wire. It's got a current going through it. So I know there's a magnetic field here. Let's draw the magnetic field. Okay, I'm going to draw it for you. And I know that the magnetic field around a wire is a circle. So I'm going to draw it for you right there. There it is. And actually, they've drawn for you the magnetic field at this very point here. It would be tangential to the circle. It would be 90 degrees to the distance from this point here to the wire, or the radius of the closed path we're talking about. This closed path is in green here. All right. So where this closed path is, there also exists a magnetic field. So let's just let that sink in. Now, the next thing I want you to think about is I want you to imagine this green closed path divided into little segments called delta L. Little segments called delta L. And if you add up all of these little delta L's, you'll get a circumference. That's what they're saying here. So where this magnetic field is here, there is also a little delta L there. They're everywhere. You add them all up together. If you sum up all the delta L's, right? You've seen the summation function in math, I hope. If you add up all the delta L's, you get a circumference. All right? That's what you get. So what they're saying to you here now is they want you to add up a bunch of multiplications. Look what it says here. The sum of what? The sum of products. They want you to add up a whole bunch of multiplyings that you do. What multiplying are you going to do? Well, you're going to multiply the little segment delta L by the scalar component of this magnetic field that is parallel to delta L, which would be tangential. Parallel to a small segment of a circle is tangential. So that's what they're saying here. Look, sum up multiplying the parallel part of the magnetic field's scalar magnitude component times a whole bunch of those little delta L's. Now, what did Ampere figure out? He figured out that when you add up all these products, so what you would do is magnetic field here times delta L, magnetic field here times delta L, magnetic field here times delta L, magnetic field here times delta L. You'd go all the way around the circle. And you do all these products, all these multiplyings, and then Ampere says, add them all up. And what he discovered is when you do the adding up, the summing of all of these products, look what he discovered. It is directly proportional to the net electric current passing through the area enclosed by the path. So what he's saying is that this left-hand side is proportional to how much current you have passing inside your green circle here, inside your closed path. And in order to change it from a proportionality to a full-blown equation, a constant is needed. And this constant is the Greek letter mu, which is their version of m, mu, okay, mu, not meow, that's what a cat says, mu, and it is called the permeability of free space. And here's how much it is. 4 pi times 10 to the negative 7 Tesla meters per ampere. So now we've got an equation, right? Because if I sum up all the delta L's, right? Well, summing up all these little bits just gives me 2 pi r. That's what they've done here. So I rearrange this equation and I get that the strength of the magnetic field right here, when it's R away from the current carrying conductor, is equal to, so the strength of that magnetic field, notice there's no vector sign in here. This is totally scalar. We know we get direction by using our right-hand rule. Is equal to the permeability of free space times this fraction. How much current do you have moving through there? All over 2 pi r. Now listen, I'm going to be very honest with you. This is your second physics course. Do not freak out if you did not follow all of this. This is actually called a path integral. You don't learn about this till university, okay? But I do want you to know this equation and know how to use it. So it basically has been reduced to a little bit of plug and play. All right, it's nice if you could follow this a little bit. Don't get me wrong. And if you're going to be moving into the engineerings, especially electrical engineering, but any engineering, because they do want you to know some electrical and magnetic field theories, then you are going to have to learn how to do some serious calculus. But for today, right here, okay? Next. Now, Ampere said you can use my law for anything. So it doesn't have to be a straight wire. It could be a coil. A coil with a certain length L, right? A coil with a current going through it. So this is a cross-sectional view of the current. So right here, the current is flowing into the page, then back over here, think 3D. It would come around, come out of the page, and back out you. So this is definitely a cross-sectional view of a coil. We drew so many of these in grade 11. Do you remember? Let me do this in a different color, right? And we'd go boom, 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 and then it would come back over here. Okay? So this is just a cross section of that. So Ampere says, look, if you draw a path again, now the path is not a circle, but it doesn't have to be a circle. If you draw a rectangular path, look at it. There it is. I can tell you the strength of the magnetic field along this side of the path by knowing how much current goes through here. And so Ampere's law applied to a current is equal to mu naught, that new constant, N. What's N? N is how many turns, how many windings we have. So here would be 1, 2, 3, 4, 5, 6, 7 turns in here. 7 turns within this length L. So that's what N is. I is how much current is actually in that coil. And L is, well, how long is the coil? Okay? So once again, kids, this is what we're focusing in on right here, the final equation. If you want to find out the strength of the magnetic field inside a coil, here's the equation. Don't worry too much about all this calculus stuff. Your time will come with that. All right, let's focus on the important for our level of study. All right, we're back. So let's apply what we just learned from our friend Ampere to what force would exist between two wires carrying a current. Now, I've added this interesting video that helps you visualize everything we're talking about. It's actually a very good video. It's from Crash Course. It's really good. I've added a link to it, so I strongly suggest you watch it. But here's the situation. You got this wire right here, okay? And this wire right here is L meters long, and it's got a current in it called I2. And a distance D from this wire with current I2 in it is another wire. This other wire here has a current I1 going through it. It is also a length L. Well, kids, think about this. If you've got wire with current I1 in it right here, a magnetic field is going to be created outside of this wire right there. This wire with a current in it is going to be creating a magnetic field, and it's going to be circular all the way around here. So what we're saying is the following. Where the wire I2 is with its current, it is interacting with the magnetic field from wire I1. Well, if you got a magnetic field and it's interacting with a current carrying conductor, there's going to be a force on it. There's going to be a force on it. So the magnetic field from wire 1, here it is, B1, interacts with the current here, I2, for a force to be created on this wire. And we could do the whole reverse thing here. The magnetic field from I2 is going to create a magnetic field where the wire I1 is, and it's going to feel a force. And you would use your right-hand rule to find the direction of the force. Look, use your right-hand rule here. Your thumb is going to point along I2. Look at the arrow here. Your outstretched open hand fingertips are going to point up the page, B1. Where's your palm? Your palm is pointing towards the other wire. So that's where we get the direction from. But to get the magnitude of it, we have to do the following. First, how strong is the magnetic field B1 there? Well, from what we learned from Ampere, B1 is mu naught, the current I1 that caused it, all over 2 pi d. D is how far is the magnetic field there from its source, from the wire. So that's what the strength of B1 is right there. Then we know how to find the force on a wire that is experiencing a magnetic field. It is I2, how much current is in that wire, L, what's the length of that wire, B1, what's the strength of the magnetic field that this wire is experiencing, times the sine of the angle between the current and the magnetic field. Well, kids, the current is this way. See the red arrow? The magnetic field is up, right? That's the sine of 90. The sine of 90 is 1. So this just reduces to F2, the force on the second wire is equal to the current in the second wire times the length of the second wire times the magnetic field from the first wire. But you see here where there's B1, I have an expression for B1 right up here. So where the B1 is, I'm going to replace it with this expression right here, and that's what I've done. So I get I2 stays the same, L stays the same, but instead of B1, I put this expression right here. And now I have the force on the second wire is equal to the current in the second wire, the length of that wire, the permeability of free space, I2, excuse me, I1, the current in the other wire, all over 2 pi and how far apart the wires are, d. It's usually not written like that. It's usually written like this. Okay, force 2 is equal to mu naught I1 I2 L all over 2 pi d. That's usually the way it's written. And more so than that, a lot of times they report this force as a force per unit length. How much force is on every unit of length of those two parallel wires? And then it becomes this equation here, and then the unit is newtons per meter. All right, so some interesting stuff here. I did post that other video from Crash Course. I really would like you to watch it. It's good for you. Today, we're just going to focus in on trying to learn this. No questions. We're just going to let these concepts sink in. You're going to read the textbook. You're going to watch that other video. Maybe you're going to go through my video more than once, slow it down, rewind it, see what I was saying, and let this sink in. I'll give you some questions tomorrow. No problem. I don't mind giving you questions. Okay, well, have a great day, and we'll talk to you later. Bye-bye.